We are now going to have a look at a few examples of using the PARFOR loops. You would have downloaded the example scripts and extracted them to a directory where you will be working at. And I am pointing to those directories at the moment. And so the examples directory, there are a couple of subdirectories there, Windows and Windows Watch. I will be working under the Windows directory, and under there are 4 further subdirectories, and each subdirectory is related to the part that we are going to be working with. There are 4 parts to this part 1 course, and the examples for each part is embedded in those directories. So the first part is to do with the PARFOR loop, so we're going to have a look at those. And the first example I'd like to show you is the PAR example 1. So can double click on that. By the way, going from one directory to another, you need to make sure that you double click on it, and otherwise you might remain still in the directory one above. If you are not certain which directory you are in, you can always type the pwd command, print working directory, and it will tell you exactly where you are. So let's have a look at the PAR example 1. Right, we are now going to try to run these very trivial examples. You can see that we had already shown you in the slides the PARFOR loop involving calculating some assigned function. There are 1024 points on there. So we are going to attempt to run that in parallel. Well, this was a for loop originally, something like that, and now we added a par in front of it, and it's just become a for loop. And there is nothing untoward within that thing. There should be it should be acceptable as a PARFOR structure. If it isn't, MATLAB will usually let you know. Now, if there are no if there are nothing started to run the parallel program before, there is no pool of workers, then hitting the PARFOR instruction will automatically start them. Unfortunately, I've just noticed that before I started giving the demonstration, I had already started the PARFOR loop. Let me just try to close it for you. Shut down the parallel pool. There we are. I've shut it down. So as to get you to a point where you'll see how PARFOR instruction will automatically start a PARFOR a pool of workers. So one other thing to comment about the structure of this script is that you will notice that it is in various sections. So this is the section highlighted. That was the first section, which was nothing going on there. And this is the next section. So the section, it is very easy to divide your script into sections by simply putting command lines which start with $%. As soon as a $% is seen as the first 2 characters of a command line, MATLAB will determine that that is the start of a new section and end of the previous section. So what is the advantage of it? We can run our script a section at a time and observe what is going on in between those, which is very useful. And there are actual icons for doing that. If you look at the top here, you see run section. We'll run the section that's been highlighted at the point that you click on that. Or there's a run and add once, which will run that section and go on to the next section, so to speak. So let us start with this section and we will attempt to run this section. Now, the bottom left-hand corner indicates us whether there is any parallel pools running. You can see when I move my mouse on there that there is, it's telling us that no parallel pool is running. As soon as we say run section, I'm going to watch out what's going on there because it will be starting a pool. What will it start? It will be starting a default pool. So there are ways of determining what type of pool you want, and you can configure your cluster profiles, but there's a default cluster profile. You don't really need to define anything as soon as you install MATLAB. If you don't, it will assume that you have a default cluster called local, and the number of workers in it is equivalent to the number of cores that is available on your computer. After all, what we want to do is to have a worker running in each of the cores. That is the most efficient way of parallelizing your program. Right, let us say run section now on this. Okay, I've issued the run section, and you can see now starting, it's saying starting the parallel pool, and it's also told us that starting the parallel pool. I had earlier on shut it down, that's what it is. Well, my default cluster was, I had named it medium earlier on, and that's why, right, there it is. It started it, and it is telling us that there are 4 workers in this cluster. And also after that, it has actually done the calculations, which is here, and produced the results A in there. And I can confirm that A is correct. If I do plot A, that should give me a sine wave. Right, there we are. So I'll close that graphics window. We don't need it anymore. There are a couple of other things here I have forgotten to tell you about. It told us how many seconds has taken to do the calculations. Well, which calculations is that? Well, let's have a look at our script. And this is where I introduce you the tick and tock commands, which are really, really useful. It's like a timer, really. Basically, you want to calculate the time taken in a section of the code, then you enclose it in this tick and tock calls. So the tick starts the timer going, and then tock stops it and tells us how many seconds have elapsed between executing that and executing that, i.e. how much time we've spent inside there in that thing that is bracketing by tick and tock. So as you can see, it has actually, taken how many seconds? 27 seconds. Now I'm going to run that again. So I'm still in that section. I'll say run section, and it seems to have run it much quicker this time. And now it's telling me that it has taken 0.48 seconds to run it. So why was it 27 before and 0.48 now? It's because, remember that it had to start a parallel pool because there wasn't one available. So most of the work was spent actually on starting the parallel pool, which is an overhead we could do without. Therefore, the lesson is that if you are going to do parallel work during a session, you start up your parallel pool and leave it running, so that you don't have to spend time waiting for it to be restarted each time you need it. Okay, let's go have a look at later on during this the next section. The only thing introduced in the next section is the GCP command, which we are going to cover later on. That tells us the current computing pool and gives us details about it. So I could say GCP, and that will give me its properties. So you can tell it's connected through number of workers 4, and I had called the cluster medium, it tells us. And there is this thing called idle time, which is when you define clusters, you can specify how many minutes that uh, parallel pool should be open, waiting for you to do any parallel work. So if it is stand idle, in this case for 30 minutes, it will shut itself down automatically. All right. So we can close open parallel pool in a different number of ways. As I had demonstrated without having the intention to do that, I can click on here and say I want to shut down the parallel pool as that, like that, or I could say delete GCP, and that will shut down the parallel pool. So you can see there now that it says it's busy, and it's telling me that it's shutting down. So it takes for a while to shut it down as well. So you can see. Right. Let's have a look at another example while we are at it. And this time, the example will tell us what we can and we cannot parallelize. We're not going to run it, but I will go through the script and show you what it is, the important aspects of it. Let's have a look. I think that's par example 1b, the next script. So the names of the scripts are named in the sort of this ascending orders, so you know which example you need to run before which one, just to make that easier. So here are some example scripts, and I'll let you run this in your own time and try to parallelize it as well. But this is showing you valid and invalid PARFOR loop constructs. We did talk about it in the previous examples and the video that not all for loops can be parallelized, but this was a for loop which could have been parallelized. So it was like 4 and like this, and I put a par in front of it, PARFOR, and it will work. So within a PARFOR loops context, we have a way of categorizing variables, or the MATLAB has a way of categorizing variables. And in this case, for example, we are calculating a variable called a, and because we've calculated it inside this PARFOR loop, it hasn't been defined outside it. It's the first time we're defining it. It is called, it's categorized as a temporary variable within the for loop. and it gets created each time round this uh, for loop index. So that a is a temporary variable. Now I have this particular assignment following that. I'm using that temporary variable now, a, and I am defining an element of an array called outside by using the element, corresponding element of another array called signal, and adding to it the temporary variable I had calculated for just for that value of the par loop index. So again, in this case, signal, it says, is a sliced input variable, or signal is really an input variable. When it says slice, that I think this is making it a bit complicated. It does say slice because we remember that this PARFOR loop is going to be executed by a number of workers. And in our case, we had 4 workers in our cluster. So therefore, uh, for each worker is going to use a certain section, certain slice of the signal array. And signal was calculated before, as you can see here. It was calculated outside the loop. But what is important is that the value of signal is not changing at all within that PAR4 loop. So that is fine to use arrays that are and reference to all sorts of elements of it in some complex ways with complex indices used, providing that array's value is not changing throughout the entire PAR4 loop, which is the case. We haven't got if we had an expression here which said signal something is equal to something, signal appeared on the left hand side, then we'll be in trouble. As it is, that's perfectly okay. So that will also guarantee that we can parallelize that for loop. And finally, we have a summation here, which entered with sum r equal to 0, and we are simply summing the value of that variable that we've been calculating. Yeah. So, and that has been accumulated. Again, that is also shown in the earlier on sections, that is also allowed. And what will happen is that each worker will calculate its own sum and then will send the results to the main MATLAB program, and it'll sum those subsums which has been sent from the workers. So if there are 4 workers, there will be 4 subsums, and they will be added together to find the final sum value. Now, by the way, of course, I need to tell you a bit about how. Let me try to demonstrate to you that we have actually got genuine MATLAB workers running at the background. Of course, it's telling us that we have got 4 workers running at the background here, but how do we know? There's another way of finding it. I will start the task manager, and if you look at the task manager, and you will see that MATLAB will have, at the moment nothing is running, so we have got some Java things that drive and start the MATLAB executable workers running. So let me just run something quickly. Let's have a look at let's run this again. So I've run that again, and look what's happened now. We've got 5 instances of MATLAB running. 4 of them are the workers, and one of them is actually what is called the client, our own MATLAB uh, program. Okay, so we have got so each one of these is a mini MATLAB in itself. The only difference between the MATLAB client that we are using here, so this is our MATLAB client. We can only communicate with the MATLAB client. The MATLAB client sends works to the workers, okay. But the workers cannot do any graphical output. So, so the MATLAB workers are basically sort of cut down versions of actual MATLAB itself without graphical capabilities. Well, so let's carry on with our example, investigating it. I mean, this one is more or less similar to the one we have demonstrated. Here we were just referencing one element of signal. We are referencing multiple elements of signals for different indices. But as I say, as this signal is not changing, and it's perfectly legitimate to do that. If a signal because it remains constant throughout the PARFOR loop. So this for loop can be turned into a PARFOR loop by putting a par in front of it. So, and let's go have a look at the things that might not be parallelized. There is something else here, actually, that I need to tell you. This is rather an odd thing, but it stops us parallelizing the loop, but there is a solution to it. So here, A is temporary, but we've got A1 and A2. They are, so A is not a constant, but it is actually an array of 2 elements, and we're setting it different values here. And the MATLAB is not going to parallelize this. And it's telling us why it can't parallelize it. If I hover around, it says PARFOR loop cannot run due to the way variable A is used, and you can get further details of example of it. So you can study these in your leisure, but the solution is also given here. What I do is I am creating A at one stroke here, both the elements, and that will then allow it to be parallelized. And then there's another thing about the structures. You cannot define access elements of and define elements of the structures unless you have defined the structures within the context of the for loop. Then you can parallelize it. So again, the solution is given here, where I said C data is a structure, so I define it as to be a structure. So it just comes into existence within the PARFOR loop. As it comes into existence within the PARFOR loop, it will allow it to parallelize. And finally, this example is a good example of telling you that there is a loop dependence here. The xk value of xk will depend value of xk minus 1 from the previous loop. And that will then because we are running these in different workers. So basically what happens is that we've got 4 workers, remember, each worker will run, say, about quarter of the work on its own. So these workers will be working in parallel. So we never know whether a particular uh, while xk is being calculated, had xk minus 1 had already been calculated or not, because it only will be calculated if it was run in serial. But when it is run in parallel, you don't know whether k equal to, say, minus k equal to 3 loop will run after k equal to 2 loop. So that is why it will not be parallelized. So, okay, I think finally I just want to show you the beats command, beats script. We are going to work with this beats script throughout our use this as an example throughout the course and show different ways of parallelizing it. So it is best to be familiarize ourselves with this, and it basically calculates a wave function. There are nested for loops here, as you can see, and then it plots it. Maybe I'll just run this to tell you what it is. This is a for loop, so it will, although we've got these workers sitting at the background, they will remain idle because there is nothing parallel in here. So I could simply click run and it will run it. And those 4 K1 to 4, all those wave patterns are plotted, each one of them. So what we are aiming to do is to parallelize this, and there are, by using the PARFOR loops. Now these are nested for loops, so you remember that you cannot have nested PARFOR loops. So we shall have to decide which one of these for loops we need to turn into PARFOR loop. And that is actually given, those examples, in B's parf1 and B's parf2 scripts. So I want you to study them and run them as examples. So that will then conclude our work with parallel for loops, and we will next move on to SPMD structures. So we'll call it a day for now.